This is the story of man's attempts to measure the tremblings of his earth. It is the story of men and women working quietly, unassumingly, and carefully in a program of research which will increase our understanding of the earth beneath us. You'll find no raging sounds in this story, no crescendos of thunder, no grinding of machines or clanking of steel on steel. It is the story of listening, minute by minute, day by day, season by season, to the heartbeat of a world. This is the story of silence, of calm and patience, of intricate, thoughtful work, moving steadily with regularity and precision. This is the story of the United States Coast and Geodetic Survey's worldwide cooperative standard seismological research network. This is a view of our Earth, and it is here our story begins. The 5 major parts of the Earth are the inner core, the outer core, the lower mantle, the upper mantle, and the crust. The crust is very thin. It's within the crust where most of the events occur that are of interest to us. This crust is made up of layers of various kinds of rocks. Here we see one stratum of rock beneath the Earth's surface. These rock beds are constantly subjected to forces originating deeper in the Earth. And there are points along a stratum where the rock is weaker and perhaps has broken before. Such a point is called a fault. Here, the rock stratum has broken along the fault. When this happens, energy is released which travels as seismic waves outward in all directions. A seismic detector located on the Earth's surface receives and records these waves. Seismic energy may be released in other ways. An underground explosion, for example, will also generate waves which may be detected at a seismic station. And the more seismic stations that detect a particular seismic event, the clearer picture we have about what actually happened. Since the turn of the century, there have been seismic stations in many countries around the world. The instruments, however, were frequently different, and the records they produced were difficult to compare one with another. Records were incompatible. Standardization was lacking. With the initiation of the Coast and Geodetic Survey's worldwide network program in 1960, we now have a large number of stations with standardized instruments making standardized records. It is easy to understand that these instruments, placed at different locations but with similar characteristics, are providing the scientific community with a valuable research capability. And with essentially uniform records, seismologists are now able to compare records of an event as detected by a number of seismic stations around the world. Here is another view of the Earth. Each point of light on this map represents one of the stations of the worldwide seismic network. As we follow the pointer, we may begin to appreciate the vast scope of this program. The ordinary and the extraordinary seismic phenomena which occur under the ground beneath us are the heartbeats of our world. Each point of light you see here is a sensitive ear listening patiently and carefully recording each of those heartbeats. From these records, we gain new insights into the physical makeup of our world. From these records, too, we can often tell whether an event is a rumble of nature or the result of man's own inquisitiveness. The $20,000 to $30,000 which the United States government has spent equipping each of these stations seems a small amount indeed when compared to the potential benefits of knowledge which will eventually accrue to us as a direct result of the existence of this vast network. There are 125 cooperating stations around the world. The equipment for every station has been donated and installed by the Coast and Geodetic Survey, and the personnel at each site are trained to maintain and operate it. There are no strings attached to this equipment, only the expectation that the stations receiving it will cooperate in the research program and make all data collected within the network available to all other participants. Seismic instruments are generally installed in underground vaults and, where possible, on solid rock. They are carefully crated and shipped to the site, where they are taken into the seismic vault. This particular vault has been blasted out of solid granite and prepared for the instruments by constructing a level floor and providing electrical power. The instrument package, as it now stands, represents an excellent trade-off between cost and efficiency. Basically, the standard instrument package consists of 3 short-period seismometers and 3 long-period seismometers. Short-period seismometers are instruments which sense the relatively high-frequency seismic energy waves. Long-period instruments are those which are sensitive to low-frequency waves. Both types of seismometers are required because the seismic energy spectrum is a broad one, and it is necessary to record a significant portion of this spectrum. Each set of 3 contains 2 horizontal and 1 vertical instrument. This permits the recording of seismic activity in all directions of Earth motion. In addition, there are 6 galvanometers, 1 for each of the units, and 6 photographic drum recorders, 1 for each of the units. The combination of these 3 elements, the seismometer or sensing device, an amplification unit, a galvanometer, and a recording device constitute a system which, when taken collectively, is called a seismograph. The equipment was designed and manufactured by various private industries. Included among these were the Geotechnical Corporation, Spring Nether Instruments, and United Electrodynamics. Texas Instruments provided the Coast and Geodetic Survey with professional geophysicists. The records which these seismographs provide look essentially like this. The recorders try to maintain a straight, continuous horizontal line. Any movement of the Earth's crust causes a deflection of this line. Most of the deflections represent Earth movements which are microscopically small, so small, in fact, that the thickness of a human hair would seem large by comparison. Examining records of the same event, taken at several different locations, permits placement of the location of the event with considerable accuracy. The cost of initiating and implementing the standard network program was over $6 million, a figure amazingly low when the vast scope of the network is considered. The establishment of the network represents a phenomenal team effort between governmental agencies and private industry. Indeed, the greatly accelerated interest in seismology, which the establishment of the network has generated, has led industries like geotech to undertake private research programs in the development of new and improved seismic sensing and recording equipment. Completing the package is the control console, which contains an emergency power supply in the form of batteries stored in the base, a radio timer, various monitoring instruments, and instruments for controlling the power supply. Incorporated in these instruments are the best features of equipment used in seismological stations. Minute by minute, day by day, the stations listen, patiently recording what is heard in the silence of the Earth. Each station manned by trained personnel who wait and watch and listen. Most of the stations in the worldwide network are operated by education institutions. The University of Michigan at Ann Arbor, Michigan, maintains a station typical of those of the network. Located in the university's botanical gardens outside of the city, the station is removed from many of the man-made noises which would make the detection of sounds from within the Earth difficult. It's a quiet job and a lonely one. There is little romance or glamour involved in the manning of these stations, Situated as they are in all corners of the earth and removed from civilization wherever possible, the seismologists and technicians constantly face problems of extreme cold or heat. Yet the men go about their daily tasks of maintaining and collecting records with only the barest regard for their personal comfort. Periodically, and regardless of the time of year or the weather conditions, the men enter the seismological vault where the sensing equipment is mounted on concrete piers. Every piece of the delicate equipment must be operating perfectly. Without such attention to detail, the records, which are collected continuously over a 24-hour period, would be virtually worthless. These daily checks are of critical importance to the smooth and efficient operation of a station. Nothing must be left to chance. It costs about $20,000 to $30,000 to equip one of these stations with the standard equipment package. Compared with the importance of the information provided by the stations of the worldwide network, the cost of the equipment package is almost incredibly low. As the men at the stations faithfully collect their records and send them daily to the network's Data Analysis Center in Washington, one can sense the pride which is felt by these men in being a part of one of the most important seismic research programs of the century. This is the story of men and women working quietly, unassumingly, and conscientiously. It is excitement generated in stillness and knowledge emerging from carefully studied analysis. From all over the world, records collected at the standard stations are sent to Washington, D.C. to be photographically copied, analyzed, and filed in readiness for all scientists cooperating in research programs. This is the task of the Coast and Geodetic Survey's Seismological Data Analysis Center. The drama of silence found at the stations seems to be intensely reflected in the work of the individuals at this center. Here, an intensive research effort provides support to theoretical research in travel times, seismic event magnitudes, hypocenter location, and seismic energy studies. A staff of 10 geophysicists, 16 technicians, and 10 clerical people process thousands of seismograms each month and fulfill hundreds of requests from cooperating scientists for copies of particular seismograms. But the center is more than the patient work of individuals at desks. It is a facility for processing, analyzing, storing, retrieving, reproducing, and providing quality control of the seismic records generated by the many stations participating in the worldwide network. More than $600,000 worth of photographic and quality control equipment assures copies of records so accurate they are completely indistinguishable from the original. This equipment is in the hands of highly skilled personnel who operate under conditions where a single speck of dust might make a substantial difference in the interpretation of a seismogram. A large quantity of research data gathered by the worldwide seismic network arrives at the Data Analysis Center by airmail. All records are screened for completeness and quality. Deficiencies are noted at this point and are eventually corrected. After the seismograms are carefully logged in, they are delivered to the staff seismologists for more complete analysis. During this phase of the operation, geophysicists examine the records, checking for completeness of resolution, focus, magnification, intensity, time marks, and completeness of stamp data. The magnifications listed are also checked and recalculated using the constants given on the face of the seismogram. These and other functions performed by the Data Analysis Center would have been impractical prior to the organization of the worldwide network. Now, however, the cooperating stations provide compatible records through the use of standardized equipment. No such compatibility existed before the network came into being. After the records have been carefully examined, They proceed to the photographic department for recording on 70mm film rolls or for reproduction on 35mm rolls. The cameras used in this operation were specially designed and built for the data center by the iTech Corporation. This high-speed, high-resolution panoramic camera makes 2 sweeps of each seismogram, producing 2 photographs of each record. Records from a particular station are brought into the photographic department. Special care is taken to keep this room free from dust and dirt. Actual photographing of this seismic record is a 2-man operation, requiring a machine operator who runs the camera and his assistant, a seismological data clerk who verifies the logging in and who proofreads the number which the operator has put on the seismogram to be photographed. About 2 minutes are required for the camera to complete its 2 sweeps of the chart. Operating on a round-the-clock schedule, the center would have a capability of processing almost 1,500 records a day. The film on which the 2 photographs of the chart have been made is processed in the center's darkroom facility. The processed film must now be cut. It is delivered to a facility specially designed for cutting the 70mm film into metered chips. These cut chips are stored in the center's archives, where a double filing system is used. This means that when requests are being filled, one file can be used by the staff and the other by visiting scientists who wish to use the viewer for special analysis. Requests are set up so that they are handled on alternate days according to the index most applicable. Scientific requests for particular recordings come to the center frequently. To fulfill these requests, the film chips of the requested records are brought to this enlarger printer. This printer makes a full-size paper copy of the 70mm chip. After the paper roll has been fully exposed, it is taken to a paper processor. The paper is led through tanks of various chemicals: developer, fixer, and bath. Various alternatives were established for furnishing copies of records to requesting agencies. In the anticipation that many organizations would want a complete file, the center makes contact prints of the entire 70mm rolls in response to standing orders. In addition, similar copies are provided on 35mm rolls for those who have 35mm viewers. After the paper has been developed, it is fed automatically into this room, where it goes through a bath and then through the dryer. The resulting copy is indistinguishable from the original record. The print comes from the dryer, completely processed. It is then passed to the cutting table, cut to the standard size for seismograms, and passed through the window to the shipping clerk, who packages it for mailing to the requesting scientists. There are no raging sounds in this story. No grinding of machines or clanking of steel on steel. Only patient, thoughtful work, moving steadily with regularity and precision. If there is a single laboratory which might be called the nerve center responsible for the smooth and efficient operation of this vast program, it is the Coast and Geodetic Survey's own seismological laboratory near Albuquerque, New Mexico. Carved out of the Manzano Mountains on the Isleta Indian Reservation, the Albuquerque laboratory carries on its dual functions of participating station and troubleshooting headquarters for the worldwide network. Each day's mail brings requests for information or assistance from stations all over the world. A timing system fails in Copenhagen. Excessive dampness at a South American location interferes with accurate recording. A module in Ethiopia needs replacing. An Australian station requests technical assistance. Some of the problems will require that a man be sent to the station site. Others can be taken care of here. Each problem or request receives careful and immediate attention, and every attempt is made to render the necessary assistance. Some of these are relatively simple. Others require the combined efforts and knowledge of the laboratory's well-trained staff of technicians, geophysicists, seismologists, engineers, and research personnel. This was the first of the worldwide network stations to become operational. As a laboratory, it remains today the most important. It was here that the 14 teams of installers were trained to set up the equipment at sites throughout the world. And it is from this laboratory that the maintenance men are sent on their annual inspections of these sites, at which time less urgent adjustments and modifications are made. The physical plant at Albuquerque is well equipped to handle the maintenance and supply functions for the worldwide network. At this location may be found a well-equipped electronics shop, a completely equipped instrument shop, warehouse facilities, and a research group where all equipment and modifications are carefully studied. In addition, there are 2 surface vaults where various types of seismometers may be carefully tested. If necessary, all of these facilities and the men who staff them will be directed to meet the requests or answer the questions which come from participating stations. Most of the problems and requests deal with equipment, either malfunction or a need for information dealing with some specific operation. The man in the electronics or in the instrument shop can usually supply the needed answers or information. Sometimes, however, the problem is of a highly theoretical nature. When this is the case, it is brought to the attention of the research group. The uninterrupted sequence of recording of a seismic event is absolutely essential if we're to come to a thorough understanding of the nature of the event. The constant attention to service by the personnel at Albuquerque makes this possible. Such is the skill and experience of the personnel at this station that problems are for the most part dealt with swiftly and competently. The effectiveness of the program is impaired when one of the stations is not operating. It is a tribute to the efficiency of these men that there have never been more than 4 established stations of the network inoperative at any one time. If such were not the case, a significant seismic event of the greatest importance might go unrecorded at a critical location and at a critical time. This radio receiving antenna stands as a silent reminder of the fact that in addition to its worldwide responsibility, Albuquerque maintains perhaps the finest seismological station in the world. Some of the best seismic data anywhere comes from the sensing equipment mounted in subsurface vaults in a mountain above the station. The exceedingly high signal-to-noise ratio afforded by the relative quiet of this location makes Albuquerque an ideal spot for testing new ultra-sensitive equipment developed at such places as the California Institute of Technology. Yet it may well be that the most important function of the laboratory will turn out to be the men who have been trained here to install and service the equipment. All installers sent out to the many stations must first complete an intensive training program here at Albuquerque, taught by an experienced professional geophysicist. In the weeks these men train here, several hours each day are spent in classroom instruction. During this time, they acquire a thorough grounding in the basic theories underlying seismology and geophysics. When they have completed this course, they will have an understanding of antenna theory, elasticity theory, information theory, and wave propagation theory. They will know how a seismograph works and why. These men have an extensive background in electronics and mathematics and must pass a rigid examination to prove it. But the theoretical is only half of their training. They receive extensive instruction of a practical nature as well. The comprehensive facilities at the Albuquerque site permit each man to become thoroughly familiar with all of the equipment and instruments used in the worldwide standardized network. Daily field trips to the surface and subsurface vaults provide the students with first-hand experience in dealing with equipment at a seismological site. Common problems arising in the installation or maintenance of the instruments are discussed, and the best solutions to these problems become a part of each man's working knowledge. Before being sent out to the stations of the network, they must have developed their skill to such a degree that they can assemble, disassemble, and completely reassemble perfectly a complete seismological station. It is the job of the Albuquerque Laboratory to supply the needs of the network, whatever those needs may be, and to supply them as readily as possible. Sometimes this is done with simply a letter, sometimes by sending new or replacement equipment, and in some instances, it requires a visit to the site by a trained technician. But regardless of the needed approach, the Albuquerque Laboratory has a reputation for fulfilling to the best of its abilities its obligation as a service center, a training center, and a model seismological station. This has been the story of listening, minute by minute, day by day, season by season, to the heartbeat of a world. From this calm, patient, and steady effort has emerged a highly important research program in seismology, the worldwide cooperative standard seismic network, in which these nations, states, provinces, and colonies are participating.
A primary task of Vela uniform called for the establishment of a worldwide cooperative seismological research network. In all, over 100 stations are involved, girding the Earth with calibrated and standardized instrumentation so that for the first time, the findings of any station can be confidently compared with those of the rest. The first station to become operational was in 1961, the U.S. Coast and Geodetic Survey's Seismic Laboratory in Albuquerque, New Mexico. 21 months later, this modern equipment was operating in 48 countries and territories. The Albuquerque Laboratory is a key link in the network. It supplies station equipment, trains geophysicists for installation and maintenance of other stations, repairs equipment, and provides troubleshooters for station difficulties. The basic equipment for each station consists of 3 component seismometers, recorders, a timing system, calibration system, copying equipment, and a power source. Package cost, approximately $20,000. Free to each station with no obligation beyond maintenance, operation, and free exchange of data. Another major task of Vela uniform has been the planning, building, and operation of advanced prototype seismic observatories in the United States. These were specifically designed to detect, identify, and locate nuclear explosions. There are 5 of these stations located in low-noise areas to take advantage of seismic signals from past and projected underground explosions at the Nevada test site, at the New Mexico site near Carlsbad, and in the